is dense or not dense. It means if you are dense or not dense plasma, depends if you are inside or outside the divided length. Most of the time, you're outside, you say you have a neutral plasma and some correction of production of electrons. It's easier.
I guess from the point of view we're normally doing, everything is ionized and the neutrals would be the addition. But you're saying if there's more ionized stuff than neutral stuff, then one just treats everything as ionized anyway. And in the cases where you worry about both, the ionization is, the ionized part is the minority, right?
Yeah. But that's probably just minor issue. So I think it shouldn't be too hard to actually get it done with. And then the radiation part, that of course is completely ready in the code. And that's sort of due to Toby, who also doesn't pay attention. Toby.
No, I didn't.
So that's in place, of course, right? Even with the 1 minus extra, probably. No, that you don't have, of course. But you have, it's just an extra opacity module for us. You have already 3 or 4 different opacities. So they're just switching opacity.
You want to go on?
You
want to go on? Or
yeah, sorry.
Well, I can go, but this was pretty interesting because I actually had some comments about these things. I maybe should have shown this first, but this is how they think. So there is somewhere out there are the stars. There is plane-like radiation. There's the initial cloud, and then there is some kind of other heating caused by some ultraviolet radiation, but that's the situation there. Anyway, there are other things is that they had this heating rate which is caused by the ionization, which I'm still sure about how this should be in pencil code, because I'm trying to still be more familiar with the alphabet with the code, but there's also the same densities and ionization ratios and stuff, and then there's these stars, which is something called something that is dependent on stellar temperature. They say only it's stellar temperature, but I have no idea what kind of temperature they have been using. So, of course, I can check.
This is some sort of fix to the. I mean, the heating is an integral over the stellar spectra, where they've assumed some sort of spectrum and then made some fits with this x0. So this is some approximation which probably is okay for this particular case, but you should be worried if you use it for anything else, I think.
So you mean the second and then also the third equation you're talking about, not the first one?
The first one is also, no, the first one uses this T star.
I see, of course, that's right.
And so this,
the
the heating by photoionization is the excess energy above the photoionization energy that gets put in the gas. So you have your stellar spectrum, and so all the photons above 13.6 can contribute there, but they, depends on the shape of your spectrum how this exactly works.
Yes,
so in principle, this is integral over the amount of photons that are still available at the position where you're trying to calculate the heating due to absorption. You've lost some of them, which is also frequency dependent. And then times the energy of the photon.
Yeah, right. Okay.
But it's a very, if you can write it like this, it's sort of convenient, because this is much cheaper to evaluate than doing all this.
But what is T effective in this context. It's normally a flux, so it's related to flux. But not here, I guess.
No, the flux is in J.
Yes, right. Not even that. Phase, the average mean intensity.
Well, it's yeah.
It's the wrong moment. Flux is another moment.
But
So
at
what
least
is
they're
the
related.
effective then?
The effective temperature of the Planck curve.
For the radiation.
But you don't have it. I mean, you just have gas temperature.
No, you
No,
have
you
a
use
radiation
a star.
in that sketch that you just showed. There is a radiation field.
I
And
see.
that one is
Yeah, then I
characterized by
understand,
intensity.
yes, of course, yeah. So it is J. Yes, of course. Understand, yeah. Good.
Well, there's at least this and the ionization, this heating and the ionization part is something that I'm right now I'm trying to concentrate on. But there's also the cooling pair for this ionization thing. So there is this this cooling down. Where I think that T is the local temperature in the cloud. There are these of beta B and alpha B terms there that have some. But I don't know if I think this looks.
What do you think of that? It's also a fit, right?
There's also fit on the cooling function.
Yeah.
Yes.
That's there.
And beta B?
But it's just hydrogen recombination.
Yes. And beta B is what?
Is that
Yeah, but, okay.
so
Uh-huh.
there is
It's just one fit.
there is little okay
All right.
a little bit it would be more clear if there's
Yes. Okay.
they define a little bit more about the alpha thing. So
Mm-hmm.
so it's yes the alpha B is approximation of the recombination coefficient.
Yeah. Right.
So it uses some kind of approximation. It's called the on-the-spot approximation. Where I think, well, at least paper size that recommendations in the Crohn's level do not lead to any net effect on the change in ionization rate.
Mm-hmm.
So it's some kind of approximation.
So, next. Maybe we should continue.
Okay, there are some other physics they used, but which I don't have had the time to give any special thought. They had the guide one of these chemical. There were in the simulation there were different kind of molecules, and they for calculating it they had this sort of chemical rate equation. But I'm still quite wondering, is it from how much of it is it necessary if I'm not especially interested in the chemical composition? But that's something I will have to study more in the future. And then there was some kind of cooling which is caused by collision in the exact line radiation. Yeah, then the equations are here. I see it's dependent on O2. Amount of O2 in the cloud, but okay, these two things sound just quite something that is I'm still trying to think about. I have quite nothing to say about it right now. I said something recently, but this research started about one and a half months ago, and no, it's still going quite, like I said, it's going quite slow still right now, and I have been quite on my own for this time, so there have been no one to ask any helpful comments or something like that. So it's mostly because I'm still quite in the phase of learning how to use the code and figure out how to program something into it myself. So, well, I don't know how much else I have to say. But I can answer some questions if you have them.
Good. Yes, I think there's two types of questions that I have. One is more of a technical, the other one is more of a physical question. Maybe the physical question first. I mean, you mentioned that Yossagam found this rigid rotation in the trunks. That could maybe be something that one could try to see whether that's something natural or whether it's something difficult to achieve. And what do you think?
With these simulations?
Yes.
Yeah, I mean, definitely you need a magnetic field. I mean, they attributed this some magnetic effect.
Yes.
Where basically the magnetic tension has spun up these things.
Yes, yes.
Which I'm not sure that many people actually believe this, but you know, in that sense, it's a very interesting project to do.
Yes,
with a code that can do the MHV.
Yes. Yes.
There is what I know there, as I have read the papers by them. I think they think that the rotation is something to do with the magnetic field.
But
What I'm
to have a collapse of a cloud, so what I have understood when I studied this, the magnetic field prevents the collapse of the cloud. It slows the collapse of the cloud. So because you have some formulas made by Chambrasica showing that it's the case. So that's the importance of the magnetic field. So I'm saying that you can do us. I had a question. What you showed about Miao, it was it was a simulation. That's right. Okay. How they deal with self-gravity initial cloud? You see, the cloud has to rotate, so it's a self-gravity system. So how they deal with this? They put just an angular velocity, or you know?
Well, at least first.
Potential or something.
My paper.
No, maybe you are not focused on this, but just if you read something about this.
Well, at least my paper, there is self-gravity. That I think is, but at least the initial cloud doesn't move. But of course, I would be just interested to see if I guess, like, if I could get at least ionization thing working, that I could try to see if there would be any effect if the cloud would rotate or something like that.
But they didn't study rotation. The Miao paper did not study rotation.
No.
They just have a cloud sitting there.
Yeah.
Is it a constant density cloud, or is it
yeah, it was constant density, or maybe. Oh, this. So this is. I think this. It was constant density cloud with. I think they had mass here.
So is an homogeneous isotropic cloud, I believe? it's homogeneous and
Yeah.
isotropic cloud.
Yeah. It's and I think that they say that they determine the value of the pressure from beta in that way that they somehow run the simulation without the ionization turned on and determine the value of beta by in which case the cloud is stable without ionization. So it's at the beginning it's homogeneous spherical cloud.
So at one point I was thinking, wow, there's so many different rather complicated physics equations, but then now I started thinking maybe they would all belong into their really natural respective modules. I mean, and there are really only 3 additional modules that would need to be invoked. I mean, not exactly only, but 3. And these would be the one that is either your neutral module or a modification of this, which would then be an ionized module as opposed to a neutral. And that would, for example, that would take care of the rate equations for NE. So it would basically be an evolution equation for NE. I mean, NE of course is just a density, but then there would be a velocity component associated with that. But I forgot about this. Is that important? The fact that the velocity of the ions move at a different speed than the neutral part?
It depends on the scale that you're trying
that
to
is
resolve.
But that is, I mean, it would be useful to include that. If once you have an evolution equation for the density, which moves as a fluid, it will of course be normally transported by the electron velocity, not the.
But if you're trying to do that, then you have to have all the collision terms between electrons and ions.
Yeah, but that would just a friction term. That's unpolar diffusion.
But you may find out that it makes zero difference, basically.
Yeah.
It's charge neutrality and basically the densities.
Okay, in that case, it would really.
Then it would be a waste of time.
Reduce the density equation, maybe. One can probably do that. One can probably say, I mean, in Anders's module, in Vladimir's module, one can probably say, I mean, there's 2 modules that go with this. There's a neutral velocity and the neutral density. And then one would say one just includes neutral density, which of course then would be rather the non-neutral density, not changing the names. The other module is ionization, and then we just have to have a corresponding addition to the opacity module. There would be one different subroutine that would be called. And then of course we have the cooling, because the cooling really comes into the chemistry module. And Steve, of course, is working on his chemistry module. So one can then have, so you asked the question, how important is it to take the chemistry into account? I mean, I looked at their papers, I think they seem to talk about 12 different species, unfortunately. And then nobody knows really how important that is. Do you know that?
Well, no, it depends on the chemistry. From the point of view of the hydro, the chemistry is really only important because it sets the cooling.
Yes, yes.
So if you want to get the temperature right, then you need to know how much there is of the different cooling species, and that's why you have to do the chemistry.
So maybe one can do it.
So it depends a bit how accurate you want the temperature to be. I mean, if you're just interested in the dynamics, you could probably get away with just having hydrogen cooling and only take into account hydrogen. Then you won't have you can't then really compare your temperatures to temperatures that are measured in the observations, because there's lots of cooling and your whole thermal model is kind of dubious. But it probably still, the dynamics of the whole process of this collapse and the outflow from will probably be still roughly okay. So it's a trade-off, because you can do 12 species or 100 species, but then you may not be able to do the calculation.
By the way, those species actually they're all rather weird. They include CO, that's okay, C1 and C2, and then HCO plus, O1, H plus, H3 plus, OH1 and OH2.
Oh,
Or it actually says OH1, 2. Strange, right? And then it says CH1, 2. And then it says M+. Pretty
It's
mysterious.
the one, I mean, OH1, 2.
Yeah, below. Yeah,
Below.
Below subscript, yes. Really bizarre.
Arabic one.
Yes, so anyway, we then has to... so if it's just hydrogen cooling, is that proportional to temperature in any sense? Is there a power law or something? Some factor times T to something?
Well, he had the recombination cooling in there. Then the collisional excitation. No, probably not a power law, but they're fitting formulas.
Oh, that is proportional to T simply, you mean then? Is that what you're saying? Except...
No, it's not. No, because it's alpha goes with T, and T is basically T. So it's a combination here of a log and a power law times.
Okay. Okay. That is of course already the simplified thing.
Yeah.
Yes, exactly. I understand. Good. I see. So I think that was useful for me at least this session.
But there are different fitting formulas for all these cooling rates. So
Uh-huh.
that, I mean, if you want an analytical expression, you can find this in the literature. There's also tables if you want. If you would prefer to do that, you can interpolate in the table. I mean, if the fitting formula becomes really complicated with different logs and powers, etc., it becomes quite expensive to evaluate for every point. So then you may be better off with a table if you have the memory.
Yes. So that actually then we come actually back to my technical question here. If I said that first that this would actually go under chemistry somehow, but now if you talk about such a simplified chemistry, it would be a bit ridiculous to call it chemistry because there's nothing chemical really in it. What we have, of course, so far in the code, there's a so-called interstellar module. And then, of course, interstellar module does indeed have a cooling curve, which is maybe not completely dissimilar. It's, of course, not at all anywhere similar, but it's at least also a cooling curve, temperature dependent, density dependent. So one may naively think maybe either you modify the interstellar module or maybe you do your own trunk module. And I'm rather thinking maybe that's not a good idea. And one should rather do different versions of chemistry modules instead. And this would indeed therefore still be good enough to count as a chemistry module, just as cooling. What do you think?
Yeah, I don't know enough about the tensile code to know how it's structured. I mean, logically, I would say you make a cooling module, which is sort of what your interstellar module seems to be. But then you make it.
But once you think of the extensions, once you really think of where the cooling really comes from, it really comes from
different
chemistry.
species.
And then in the future it would really be part of such a chemistry module. Normally, of course, the chemistry we were thinking does actually rather the heating, by the way, of course. If you think of H and O making an explosion in the atmosphere under high terrestrial pressures, then of course it makes heat rather than cooling. This is still the same chemistry.
But you're saying the radiation should be a natural component of the chemistry model. I mean, there is chemistry without radiation, but maybe in the astro context, chemistry without radiation doesn't make that much sense.
I mean, the radiation comes in addition to this. So we are talking about three modules altogether now. One that takes care of NE, except that perhaps could be combined with chemistry into one. And we have the radiation module. So the radiation module comes in addition simply because
the thing you have to worry about
yes?
a little bit is that the opacity depends on how much neutral hydrogen there is.
Yes.
And this is the quantity that is changing. So your opacity is changing all the time.
Yes.
And it can change depending on how quickly your ionization progresses. It can change very rapidly, which then, if you don't do anything special, requires very, very small time steps. That's
From the cooling is.
well, for everything, because the radiation drives the whole process.
So but maybe I didn't listen. So the time step comes from the.
Your opacity is your X is changing, right?
Yeah. Yes.
And so you have your photons coming in, let's say from the side. They travel through your grid. So you have also an integrated effect. So somewhere along this line, X is changing. All the downstream points, let's say, for the radiative transfer, you can suddenly see different amount of photons. So the time scale for which this one point X is changing is the time scale for your entire problem.
Yes.
And this could be a second, maybe, depending on how many photons you have, what your density is, whatever. And then if you want to follow this for 10,000 years, this may be a bit challenging.
Okay.
So there's this,
Yeah.
this is one of the problems you run into when you try to do this. But, I mean, there are solutions because these people also did simulations, but you have to be a little bit, well, you have to be aware of this. And
Yeah. I need to introduce Harald because we had a session where we all introduced ourselves and we were not here yet.
No.
So Harald Mellemer, he's from the observatory here in Stockholm and is working on ionization fronts in cosmological context.
Well, and also
Of course, I have immediately connection with this. So
maybe we should talk a bit.
Yes,
Because
exactly.
I may be able to. I mean, I've done this for quite some time, so I may be able to give you some help.
It would be good. Yes, exactly.
And I have lots of this. I mean, I've lots of these things coded up into little routines, which can be useful. Pencil code.
Okay.
Because I'm not actually a pencil code user.
Okay. Maybe you could become one then.
No, I did think about. I mean, a lot of my photo animation stuff I have joined with different hydro codes, so I also have some experience with that.
Exactly.
So there may be.
Yes. Very good. And in that connection, maybe then a good idea to come back on this for another time. All right.
Okay. So we move on, and let's thank Nordita again. And now